All right, so this is going over the 2018 free response, numbers 1 through 3. Your homework for tonight is numbers 4 through 6 on that same free response. 4 through 6, remember, are no calculator questions. And after we're done going over the homework here, you will work on those homework questions for the rest of the period. So we want to know how many people were in line from 0 to 300 seconds. So you're just doing the integral from 0 to 300 of the part of the piecewise function that was for that time interval, putting it in your calculator, and you end up getting 270 people. Then we want to know how many people are in line at t equals 300. There's 3 things that we need to take into account. The number of people that were in line at time 0, the number of people that entered from time 0 to 300, and the number of people that are leaving from time 0 to 300. So at the start, time 0, there's 20 people. We already found in part A that 270 people entered. Now, the people that are leaving, technically, we're doing integral from 0 to 300. And they said that they were leaving at a constant rate of 0.7. So it's 0.7 dx. Well, when you do that antiderivative of 0.7 dx, you get 0.7x, and then you'd be subbing in 300 and subbing in 0. The subbing in 0 would go away, so you're really just subbing in 300, and we would be subtracting it because those would be people that are leaving. So I kind of shortcutted that and just did what it would end up being and didn't show that integral. And in the end, that would end up being 80 people that would be in line at time 300. When you're greater than time 300, no new people are entering the line. So we're going to think of this like a linear equation. Think of 80 as like your y-intercept, because that's how many people there were at time 300. And then people are exiting at a constant rate of minus 0.7 for each t. Now, t in this sense is the t's beyond 300 as we're solving it. And then we want to know when will that line essentially end up as 0. So when you solve for t, you get 114.286. But again, that was the t's beyond 300. So add it to 300 and you get 414.286 seconds. And we want to find when there's a minimum. So I came up with an equation for the people that were in line at any time, P of t. We needed to take into account the people that were there at the start, those that added to the line, and those that were taken away. So 20 were there at the start. 0 to t of our entering expression. Now notice I have a dummy variable in there because I want t to be on top, so I use some dummy variable in place of t, so I just used x. Then minus for the people leaving, integral 0 to t, and it was a constant rate they were leaving, so that's 0.7 with some dummy variable. When you do a derivative of an integral that goes from a number to an algebraic expression, we're subbing in that algebraic expression, and then technically we're also multiplying by the derivative of what we subbed in afterwards. In this case, we'd just be multiplying by a 1 because we're only subbing in t. So you see my p prime of t there. Set that equal to 0, and then using the calculator, find those critical values. And we care about the ones that are between 0 and 300. We ended up getting 2 of them. You can use your graph of p prime to tell your minuses and pluses. Make sure you have your p prime of t and t labeled on your number line. We're looking for minimums, so we care about the relative minimum here, which was at the 33.013 seconds, and that's because p prime of t switched from negative to positive. Our interval was inclusive. It was a closed interval, so we have to check our endpoints and our relative min. P of 0 we already knew was 20. P of 300 we already knew was 80 from part B. So then we just have to do the P of 33.013. Plug it back into your original thing, we get back 3.803. Make sure you answer all questions. They first wanted to know at what time is the minimum number of people in line. So that would be at time 33.013 seconds. And then they also want to know to the nearest whole how many people are in line then. Well, because we got 3.803 to the nearest whole, there would be 4 people. Moving over to question 2. So we want to do p prime. We've got to do a product rule. So the derivative of the 0.2 So the derivative of the first part, the derivative of the 0.2 h squared would be the 0.4 h times the regular of the exponential part plus the regular of the 0.2 h squared. And then when you do a derivative of an e, it's e to the stuff times derivative of stuff. So we have e of that stuff, and then times the derivative of the exponent gives us the minus 0.005 h. We want to evaluate that at 25, so just sub in 25 for h, and to 3 decimal places you get minus 1.179. Now we need to put units on it. It says P's units in the problem were millions of cells per cubic meter. We've done another derivative, so it will be per another meter. So you could either have millions of cells per meters to the fourth, or you could have millions of cells per cubic meter per meter. That's how I ended up writing it here. Now what this is representing, it's the rate of change of the density at a specific depth. In this case, at the depth of 25 meters. So we want to know how many plankton are from 0 to 30 meters. Each cross section has an area of 3. And then that would get multiplied times our P of h. So in this integral here, let's just look at our units. The 3 is representing a meters squared. The dH is also a meters. So now we have meters cubed from those two things. The P of h was millions of cells per cubic meter. So the cubic meters coming from the 3 and the dH wipes out the meters cubed in the denominator of P of h. So now this integral is just going to add up a whole bunch of millions of plankton. And we want to do that from 0 to 30. And to the nearest million, we got 1,675 million plankton. All right, so our P of h function only went from 0 to 30. There's some other function that we use when we go beyond 30. Now, something they tell us about that other function is it stays below a third function that is u of h. So for our total amount of plankton that goes k meters deep, assuming k is beyond 30, you've got 0 to 30 of 3 pH dH. That's the same as part B. And then plus 30 to k, some unknown amount beyond 30. But when we're beyond 30, the function we're now using is f. So it would be f of h dH. That's the first thing we wanted to write an expression that represents our plankton cells. Now notice we did have the 3 in each of them because it had to multiply by the square meters of each slice, essentially. Well, now we had to explain why this is going to be less than or equal to 200 million. Well, the first part there we had from part B is the 1675, and I left the decimal parts on it because I didn't know if the decimals would play a role, but that was 0.415, so that's the first part. We know that u of h, when it goes from 30 to infinity, converges to 105. So that's that part. It also has a times 3. So the 3 times the 105, we know that integral of u of h is going to be capped at 315. Well, we know f of h's integral is guaranteed to be less than that. So we know 315 is an upper bound of that second integral. So if you take the 1675 plus the 315, that gives you 1990 million plankton cells, which stays less than 2,000. So that was a little bit of a tricky question. D was a little bit more straightforward. We just want to know distance traveled of a parametric, so it's essentially arc length. You do integral square root of the x derivative squared plus the y derivative squared. So we were going from 0 to 1 on our integral. You have square root of x derivative squared plus y derivative squared, and you got that 757.456 meters. Moving on to number 3, this was a no calculator question. To find f of -5, we have to take into account 2 things. The y value of what we know, so we know at x equals 1, we have a y value of 3, and then what's been accumulated. So initially we want to think of f of -5 as 3 plus the integral from 1 to -5 of g of x. Well, we like our smaller thing to be on the bottom, so flip those bounds and make it negative out front. So it's 3 minus the integral from -5 to 1. Well, from -5 to 1, you've got a box that's 9 underneath, you've got a 1.5 underneath, and you've got a 1 that's above. Negate all those combined like terms, you end up getting that it's 12.5 or 25 over 2. Next, we want to go integral from 1 to 6. Well, from 1 to 3, it's nice. We can see on the graph that that's 4. From 3 to 6, we're going to have to do the integral of what they told us g of x was for that part. So I squared it out and left my 2 out front. Do your antiderivative, sub in the 6, sub in the 3, and you eventually get 10. Technically, anything under this part would get you full credit, but 10 is the simplified version of that. We want f, the original, to be increasing and concave up. F is increasing when its derivative is positive. So we're looking for when g of x is positive. So g of x happens to be positive everywhere here, not including where we're touching the x-axis. So we have those as options. So that's what this is talking about. And then concave up is when second derivative is positive. Well, our graph is of the first derivative. So second derivative will be positive when the first derivative has a positive slope. So we'd have, of our blue options, these 2 sections. So those open intervals would be 0 to 1 and 4 to 6. And again, make sure you have some type of explanation. I said that the f prime or g had a positive slope. You could have said that g was increasing. You could have said that f double prime was positive there. So some different ways that you could explain it. And then the last thing, inflection point. We're looking for second derivative to change signs. Second derivative will change signs when the first derivative changes from either increase to decrease or decrease to increase. The only spot where the first derivative changes from increase to decrease or decrease to increase is at x equals 4. Because all the other places we've got periods of horizontals. So x equals 4. I set it as f prime is switching from decreasing to increasing. You could say f double prime switches from negative to positive. That would work as well. All right, any time left in the period, you have to work on the next 3 problems on 2018. Make sure to do that on a separate page. Have a good rest of your day.